And share screen. I'll share this one. Okay, so I hope you guys can see my screen. So it's a PowerPoint slide saying Introduction to Graph Theory. Let me know if you can't see it. Okay, so I hope you guys can see this. All right, so we're already done looking at particular methods from linear algebra that can be applied to data science. So at this particular point, we're looking at a specific branch of math which has many implications insofar as graph theory, insofar as data science is concerned, and that is the field of graph theory. Perhaps a quick show of hands. Who among you have experience about graph theory or who has background with graph theory? Okay, so Christian, I think has three of you raise their hands. So good. So, but for the benefit of the others, maybe I'll have a quick introduction of what graph theory is. And then towards the end, we'll try to look at graph theory in data science and some other more major ideas from graph theory that can be applied to data science. So, graph theory as a field, it started as a branch of pure math, but it is motivated by a physical problem. But let's first define what are the essential parts of or what are the objects of study in graph theory. Of course, these are graphs. Now, what is a graph? A graph is simply a pair. Some will describe this as a triple, but a graph generally consists of a set of vertices and a set of edges. Now, if you look at the picture on the left, vertices are usually denoted by dots or by circles, and the set of edges are just links or just lines joining these vertices, right? Some will label them as an ordered pair containing the vertices that they are joining together. All right. Now, and then the collection of the set of vertices and the set of edges is our graph G. More theoretical approach to graph theory will define a third component to graphs, which would be the relationship or the defining characteristic or the characterization of the edge set, or basically a criteria that will tell us when are two edges connected by an edge, where two vertices are connected by an edge. Okay. Now, mathematically, this is our graph G. It is the pair of set V, which is the set of all your vertices. In our case, those are vertices A, B, C, and D. And the second set is the set of all edges, which consists of the pair AB, BD, AD, and AC. So here we have a graph with four vertices and four edges. Okay. A graph is synonymous to networks because they are usually the mathematical objects used to represent networks, or what do we mean by networks? Essentially, things that are connected to each other. So the vertices will represent the things that you want to look at the relationships of, and an edge between two nodes in the network. So vertices are commonly referred to as nodes in the network. Two nodes will be connected if they are related to each other. And that word related will depend on the particular application area you're working on or the context in which you're doing the work. Right. And the terminology for edges there is link. All right. So, but in the course of this study, since we are looking at we're looking at graphs, networks, their application, etc., we can use these terms interchangeably, right? So I won't have any distinction between graphs and networks, vertices and nodes. Graph, vertex, and edge are usually the more theoretical terms that are used, but in application, network, nodes, and links are the ones that are used. So you can use whichever whichever terms you're more comfortable with. Okay. Now, these are some examples of networks and systems that can be modeled by graph theory. So computers in a local area network can be modeled as a graph, wherein the nodes or the vertices are the computers in the network. And you draw a link or you draw an edge between two computers if they are connected via what? via a LAN cable or something like that, right? Or it can also be used as a model for anything, right? For instance, here quite an old actually I'm not familiar with the groupings here, but I'm guessing this is something from yeah, I'm not familiar with this. So, but definitely the vertices here are actors: Marlon Brando, Henry Silva, Al Pacino, and Michelle Pfeiffer. And there's a link between them. I'm guessing this would be they will be connected if they appeared in the same movie. Hopefully, I'm right because there's a recording. If I'm wrong, please correct me. Right? Probably Marlon Brando and Al Pacino appeared in the movie The Godfather, so they are connected by an edge. Michelle Pfeiffer and Marlon Brando did not co-star in a movie, then they are not joined together by an edge. So you can model a lot of things using using graphs, right? But if you look at the green comment over here, this is where they draw the line between graphs and networks. Graphs are the mathematical objects. They are representations. They are the abstractions of these networks of things. But again, for me, they are just essentially the same. Now, these are the one on the top on the bottom right is basically what a graph is to a mathematician. It's just edges labeled 1, 2, 3, and 4, and edges between 1, 3, between 1, 2, between 3, 2, and between 2, 4. Right? But all of these three pictures that you see on the slide are basically the same things, at least from a mathematical perspective, right? So you can associate a certain node in the computer network, a certain actor in our lower left picture, with a vertex in the one on the bottom right. Okay. Now, where did the graph theory start? Well, it all started when Euler prove the classical problem of the seven bridges of Königsberg. So in this particular problem, right? So you have four land masses in Königsberg, which is now Kaliningrad, Russia. So this was broached in 1735, and the problem is, uh, can uh, can one walk across all seven bridges and never cross the same bridge twice? So basically, it's a traveling problem. So you can you come across all seven bridges without crossing the same one twice. And Euler provided a very novel approach to solving this problem. Novel in that time because he actually offered a mathematical proof that such path does not exist. And how did he do that? He used an abstraction. Right? He transformed the map of Kaliningrad or the map of the Kaliningrad, the seven bridges in the Prigel River, and convert it into this landmass over here. Let me use my pointer here, yeah, to this graph. Right, so probably you can think of this as the network. Where this one to be the network, wherein the nodes are the land masses and they are connected if there's a bridge connecting them, right? And this is the mathematical representation, which you can think of the graph. Okay. And Euler proved that there is no such path, meaning you cannot traverse all seven bridges of Königsberg without traveling at least twice on one of them. Right. And since then, graph theory developed as a subject, both in theory and in practice, because again, everything in this world has connections, right? Or almost everything in the world has connections. And again, a nice way to represent them are via graphs. Okay. Now, this is another example. I think this is the same example that keeps popping up in the previous illustrations that I have. So let's just describe some of the parameters, some of the numbers that will describe this graph. The first one is the number n, which is the number of vertices. This is called the order of the graph. So our graph G on the slide has order 4 because we have 4 vertices, namely A, B, C, and D. And then L is the number of edges. So you count just how many edges we have over here. So obviously we have 4 edges. The number of edges is called the size of the graph. So these are two parameters, the two basic parameters of the graph. Basic because they count. the elements of the pair of sets that characterize our graph. So order, number of vertices, we'll denote that by capital N, and the size of the graph is the number of edges, we'll denote it by the big letter L. Okay, so here that. Okay, now what we see in this picture is an example of a simple graph. A simple graph is a graph wherein we don't give any distinction on where an edge starts and when it ends. So basically, if you look at the edge AC, right, we can assume this to be a double-edged sword connecting the vertex A to the vertex C and the vertex C to the vertex A. So really, in describing edge AC, it doesn't matter if you call it AC and CA, because essentially in a simple graph, the direction is not important. An edge between A and C means we can start from A and end up in C, or start at C and end up in A. But there are some networks that connections work one way, or networks where the connection doesn't necessarily work two ways. For instance, we have this digraph, right? So, or in order to model them, we use digraphs. Digraphs, we look at the direction. These are directed graphs wherein the direction of the edge, the way we represent edges are very important. Okay. Now, if you look at the edge AB, right, that means it's an edge starting from vertex A and ending in vertex B. So you cannot traverse, or you cannot start from B and end up with A through the edge AB, because the ordering here is very important. That's why if you look at the edges between A and C, we wrote AC and CA separately, because again, it's a digraph, it's directed graph. It's important where you start and where you end. And it's quite interesting to look at the dynamics of both kinds of graphs, because they are used to model different kinds of networks. Right? So in a directed graph, okay, directed graphs are usually used for one-way transportation networks, right? Or by the way, before I go to the applications, I was supposed to ask you what are the parameters of this graph. So what is the order of this graph? Order, or the question is too easy, you don't want to answer, right? So here the graph has how many what's the order? The order is the number of vertices, so that is 4, right? But I think the tricky question here is what's the size of this graph? Again, this is a directed graph, so the ordering matters. So the edge AC must be counted differently from the edge CA. So here we have how many? 1, 2, 3, 4, 5. We have 5 edges. So the size of this digraph is 5, right? Now, this is important. Digraphs are important because they're used to model one-way transportation network. So if this is a transportation network, that means that you can start traveling from vertex A and go to vertex C via the edge AC and go back the same route from C to A. But looking at this, you cannot travel from vertex, say, from vertex A. You cannot travel from vertex B directly to vertex A without passing through any intermediary vertex, right? Because there is no link starting from B going to A, right? There are example email networks wherein there is an edge from person A to person B. Person A sent an email to person B. Obviously, that's not the same as person B sending an email to vertex A, right? Then in assembly lines, so you can also model that using digraphs. Usually, edges in digraphs are also called arcs, right? But again, I will stick to using edges instead. Now, key properties of nodes. Excuse me. Now, I'll be bombarding you with a lot of terms and definitions here, because we need to have an understanding of the basic characteristics of graphs before going through the algorithms. that we can that we can perform on them to get or to extract some nice information. Because when we go to machine learning techniques, there are some random trees, there are some neural networks, so they will involve some graph theory. But fortunately for us, we will not be diving to the graph theory part of the code, but at least at this particular uh, point in time, I want you to be familiar with this technique so that when the time comes that, say, in your dissertation, you need to modify some algorithms, then you have a little bit of graph theory with you to help you, right? So now let's look at the key properties of nodes. How can we describe nodes? Because the size and the order are global properties of the graph. So, but let's now look at some more local properties. In particular, what are the characteristics, the quantitative characteristics that we can attach to nodes? So, for instance, we start with the edge, with the degree. The degree of a vertex is the number of edges connected to the vertex. So if I want to compute what's the degree of vertex A, I simply need to count how many edges are there connected to the vertex A. In this particular case, we have edge AC, the edge AD, and the edge AB. So we can conclude that the degree of vertex A is equal to 3, right? Similarly, the degree denoted by K sub B of vertex B is 2, the degree of vertex C is 1, and the degree of vertex D is equal to 2. All right, everything's clear? I hope my numbers are right. Just let me know if I missed something. Yeah. So everything is just counting them visually, right? And that's the beauty of working with graphs because they're mostly visual, except whenever you have large networks, then counting will be very hard, right? So you need a computer program to give you all the key properties, right? And actually, MATLAB has a nice repository of routines that will allow you to extract the basic characteristics of graphs, including the local ones like node properties and edge properties. Okay. So now a quick analysis of the pattern here will tell us that the size L of the graph is one half the summation of the degrees. It makes sense that the degree of all nodes will give us an insight as to the size of the graph itself. But why do you think is there a multiplier one half to it? Why not just sum up all the degrees? We can verify this formula at least for this case. So if I add up the degree of the 4 vertices in our graph, I'll see I'll have what? I'll have 8. But I know that the size of this graph is only 4. So there is really indeed a one half multiplier outside. But can somebody reason out why there is a one half in front of that summation? Because this formula L equals one half the sum of the KIs is claiming that the size of a graph is half of the sum of the degrees. Why do I need the one half multiplier in front? Anyone? Okay, go Z.
Yes, I think it was answered already, sir, in the comment, but my answer is also the same. The edge is connected to two vertices, so there is a double count. So that's why we need to divide by half, if I'm not
Oh,
mistaken.
all right, thank you. That's right. Oh, sorry, Christian, I missed your chat, but yeah, you're also right because each edge is bi-directional, and if you look at it, you are counting each edge twice. So, for instance, this edge AC is counted when you computed the degree of vertex A, but it will also be counted again once you when you look at the degree of vertex C, right? So they are counted twice, so we need to account for that. So we take half, right, of the sum of the degrees, right? Okay. All right. Just a quick question. Do you see the entire slides, or is there is there something that is blocked in your screens? Because I want to keep the meeting chat floating, but I don't want it to obstruct your view of the entire slides. Okay, great. So I can leave the meeting chat floating uh, in front of the slides and nothing will be blocked. Thank you, Z. All right. So next per set of parameters that we will look at. Oh, the average degree. So the average degree can be seen as a global property because it's a property of the graph itself. The average degree, as the name implies, is simply the average of all the degrees. So we already know the degrees of each of the vertices in our graph. We take its simple average. So that's 5, 8 divided by 4. So the average degree, denoted by bracket K, is equal to 2, right? So on the average, a vertex is connected to two links or to two edges. And the formula for that, an alternative formula, is simply twice the size all over n, right? So I guess this can easily be computed because this can easily be reasoned out because the summation of the ki's, right, is basically twice the size, right? So that's going to be 2L because L is 1/2 the summation of the degrees. Therefore, the summation of the degrees is equal to twice the size. So essentially, it is 2L all over N. Okay. Now, let's look at how we do it, or how do we count, or how do we compute the degree for digraphs or for directed graphs. Now we distinguish between an incoming degree and the outgoing degree of the graph. When we say incoming degree of the ith vertex of the graph, this is the number of edges that point to vertex I. That's why it's called incoming. How many edges are going to the vertex of under consideration? So if I want to know the incoming degree of vertex A, I simply need to count how many edges are going to or are pointing towards A. So definitely the edge CA is one of them because it starts from C but it points to A. Another one is the vertex D. The edge DA. And I think that's all of them. So vertex A will have incoming degree equal to 2, right? In contrast would be the outgoing degree. The outgoing degree is defined as the number of edges that point from the vertex under consideration to other nodes. So if again we consider the vertex A and count its outgoing degree, so we need to take a look at how many edges starts from A and points somewhere else. Definitely we have the edge AC and the edge AB. So that's going to be its outgoing degree, right? Now here are, you can double check the numbers. I'll provide you a copy of the slides later, but you can verify that these are the numbers. But like simple graphs, we would like to translate the degree, the degree of a graph, the degree of nodes into a more global measure of the characteristic of the graph. So we look at the averages of these numbers, right? Now, but before that, we also take a look at the total degree of a vertex. The total degree of a vertex is simply the sum of the incoming degree and the outgoing degree. So, and this is the notation will just be simply k sub I. We drop the superscript in or the superscript out out for the incoming and the outgoing degree. Okay. Right. Now we translate it to the global property, and it seems that the size of the graph is simply the sum of the incoming degrees or the sum of the outgoing degrees. Why do you think that is so? Because remember, when we are in a simple graph, the size of the graph is 1/2 the total of the degrees. But here, this slide is telling us that that the size is equal to the sum of the incoming degrees or the sum of the outgoing degrees. So why do you think is that so? Is that so? Why is there no multiplier? Why don't I need to take the sum of the sums, right? Because if you're thinking about it, you're looking at the number of edges. Why shouldn't I add the incoming and the outgoing degrees? Or why shouldn't I just take the sum of the total degrees of each of the vertices and come up with L? Okay, great. Jihan is right because I'm only counting the edges once. Because say the vertex A, the edge AC, okay, will be counted only once as an incoming as an incoming uh as an incoming edge, right? If I count the incoming degrees of all the vertices in the graph, then AC will only be counted once. And then if I count the outgoing degrees of all of the vertices, the edge AC will also be counted only once. So it suffices to just take the sum of either the incoming or the outgoing degrees. Or if you want to involve really the incoming and the outgoing degrees, you can take one half of the sum of the incoming and the outgoing degrees. So basically, it's one half the summation of the total degrees. All right. So I hope these formulas are making sense because I will make some references to this whenever we go when we go to classification and clustering algorithms, right? Because these are parameters that we can feed into these machine learning algorithms in order to get the best model for a particular set of data. Okay. And then similarly, we can define the average degree of a digraph. It is simply either the average incoming degree or the average outgoing degree. Or in essence, it is simply the size of the graph divided by its order, right? So that's the average degree. In contrast to the average degree of a simple graph, it is twice the size divided by the order. Okay, so the formulas differ slightly for simple and directed graphs. So be careful about with the use of these formulas. Okay. All right. Now, so we're looking at the degrees, the average degrees, but another interesting aspect to this is the degree distribution. When we look at the degree distribution of a graph, this is simply the probability that a randomly selected vertex in a graph has degree k. So you'll be asking, what's the chance or p sub k if you are asked to find p sub 1? You're looking for what's the probability that when I select or draw a vertex in the network or in the graph, then I will get degree equal to 1. That's what P1 will give us, right? So it makes sense that the formula for this parameter, the degree distribution, would be P sub k equals N sub k all over N. So essentially, we will just count how many edges, or sorry, how many vertices in the network have degree equal to k. And I'll divide it by the total number of degrees in the graph. So it's a simple combinatorics problem, right? You count all the possible candidates. We have n of them, the order, but the numerator will be just the number of vertices with the desired order. Sorry, with a desired degree. Okay. So for instance, if we want to compute P1, right? So I know the denominator will be equal to 4 because we have 4 candidates in the draw. But how many possible outcomes are we looking for? So which are the vertices uh of degree 1? Remember, a vertex will be of degree 1 if there's only one edge connecting it to another vertex. In this particular example, how many vertices have degree 1? And I'll put that in the numerator. That will give me the probability. Okay, Jehan says 0. I guess you need to to revise your guess. I'm looking for how many vertices have degree 1. I think Stevens is right. Vertex C has degree 1 because there's only one edge connecting vertex C or connected to vertex C. So, and are there any other? Vertex A has degree 3 because there are 3 edges connected to it. Vertex B has degree 2. Vertex D has degree 2. So it's really just vertex C. So the probability P1 is equal to 1/4, right? And then if you compute all of the p sub i's, that will give you the degree distribution, right? So in this particular case, P2 is 1/2 because we have 2 vertices of order 2, namely vertex B and vertex D. And then P3 is 1/4 because there are there's only one vertex of degree 3, which is the vertex A. And then P4 is equal to 0 because there's no there's no vertex of degree 4. Z, do you have a question?
Yes, sir. Since the degree distribution is a probability, is the sum of all these degree distributions equal to 1?
Yes, it should be, right? So it's a probability distribution. So it's a probability. So that means the sum of all the p sub k's must be equal to 0. Okay, great observation there. But I think I have that as a remark in the slides. So yeah, take note of that or just double check with the slides. There we go. This is what Z is talking about. And it's a discrete distribution, right? Because you have discrete cases or discrete spaces in this distribution. Okay. Now, moreover, the average degree is simply the expected value, right? Here I am summing up to infinity. It's a discrete distribution. I'm summing up to infinity, but the probabilities for higher degrees, for the probabilities p sub k, whenever k is greater than what? When k is greater than the size is equal to 0. So essentially, this infinite series is just a finite sum because eventually, for large enough k's, they will be equal to 0. But that's another way of looking at the average degree. It's just the expected value of the degree distribution. Okay. So for those that are more statistically inclined, so yeah, you can remember it this way. Okay. Now, degree distributions are quite nice are quite nice properties of nodes because they will give you insights on how this particular system or this particular network behave. But I want you to ponder on this question that when or what are the practical scenarios wherein the degree distribution would be of very high importance. Okay. But I don't expect you to think of answers to this right now because probably this is the first time you're hearing about graph theory and graph distribution, etc. So I'll keep this as a floating question. All right. Now, before proceeding, let's have a 1 minute break. I'll just need to get my notes. I wrote some formulas, and I don't remember all of them, so I need to get my código. But I'll be back in a minute. All right, guys. And it's also time for you to breathe, and because there's a lot more to come. All right. So yeah, 1 minute break. Okay, so let's proceed. I just remember that I have actually a uh, a tablet that I can connect to the laptop. So yeah, I hope I can write better now. All right. So now let's look at different degree distributions for some.
Sir, can we try with the with maybe our own view on what degree distribution is important in the real world?
Oh, sorry. What's the question there about the this question?
Yes, I'm seeing the question. I
Uh-huh.
wanted to try with the answer.
Well, I want you to think about it, but not right
Okay.
now,
All right.
because again, this might be the first time you're seeing degree distributions or you're hearing graph theory at all. So I want to keep this as a floating question for now, probably after we finish the discussion, because I'll give you some examples of degree distributions later, and these applications will be much evident or much easier or this question will be much easier to answer, right? Okay, so let's look at some examples as promised for degree distributions. So for example, we look at this distribution. So here I simply plotted the degree distribution for two graphs. The first graph is represented by the histogram in black, while the other graph is characterized by the degree distribution in the gray histogram, right? So basically, we interpret this degree distribution histogram as this. So if you look at the x-axis, okay, yeah, here you go. The x-axis tells us the degree of the vertex. So if you look at this particular portion of the histogram, we're looking at p sub 5 for the two graphs that we have. So essentially, I'm looking at uh, what is the probability that a randomly drawn vertex will have degree equal to 5. So in the black graph, right, it will have probability less than 3%, right? So because this is 5% distribution probability, so roughly below 3%. So that means there's a very small chance that we draw a vertex with degree 5. While on the gray graph, it seems that that is more likely that we draw a vertex of degree 5, because the probability here is somewhere here. Probably I'm estimating around 17% or around that number, right? So we look at there's a greater chance of picking up a vertex with probability a vertex of degree 5, right? So essentially the probability distribution will give us an idea of what the average degree, right? Or even this is much powerful because it will tell us what's the probability that we get a vertex of a certain degree. Now, both of these graphs follows a Poisson distribution. Right? So, because the formula for the P sub k for these two graphs follows this formula. So it's the natural exponential base raised to negative c times c to the k over k factorial. So the probability that a randomly chosen vertex will have degree k is equal to e to the minus c times c to the k over k factorial, where c is a constant, a parameter in the model that is greater than 0. Right? So that's the only condition. Now, if I will be trying to characterize the degree distribution of the black graph, I might say that here k is much larger than, oh sorry, yeah, k is much larger than c, or essentially c is sorry, the number, because here I'm seeing that the peak, the highest probability happens at p sub 2. So this is p sub 2. So that means e to the minus c times c squared over 2 factorial is the highest among all the possible values. So I guess here the larger the larger k is, the lower the probability would be. So I'm thinking that, and you can correct me if I'm wrong, I'm trying to get some inference here. It seems that p sub k will eventually decrease, right? Especially when k is much larger than the parameters c in the model, right? because k factorial, which is in the denominator, will grow fast as k increases. And e to the negative c, remember c is greater than 0, so it will further contract the value of p sub k. So essentially, those graphs with Poisson degree distribution will most likely have very, very little amount of vertices that will have high degrees. The concentration will be for smaller values for k, right? Now, another example, oh, by the way, Poisson distributions, degree distributions do not usually arise in applications because uh, most of physical systems usually have several vertices that are connected to a lot of other vertices. So degrees can be very, very high for most physical systems relative to the size of the graph. So but Poisson distributions are very important because I think they are one of the first distributions that were used to study the topology of graphs or some geometric graph theoretic properties of graphs. So these are very important from a theoretical aspect, but not so much on the application side. So some other more interesting degree distributions insofar as applications are concerned are binomial and power law or exponential distributions. So the one on the left is an example of a graph with a binomial distribution of binomial degree distribution, right? So it shows a network with 10,000 nodes and an average degree of 10. So here our bracket k is equal to 10, and the order n is equal to 10,000, right? Now it's a binomial degree distribution because its probability, the degree distribution or the probabilities p sub k follows the following formula. So p sub k is equal to n minus 1, the order, minus 1, taken k. I hope you can still read my handwriting. I'm still struggling writing with a tablet, but it's p to the k. Oops, sorry. I can write the k. So it's p to the k times 1 minus p raised to the n minus 1. Come on. N minus 1 minus k. Right? So where p is is your parameter here. P is actually a probability of success. So p is a positive number between 0 and 1, right? So that's basically the formula for the binomial distribution. So I think here the parameter would be p, n minus 1 because n represents the order. So you should put an n minus 1 there as a parameter in the usual discrete binomial distribution. Okay. Now, usually the probability p here is not really just a random value that you choose. P usually is the probability that two random vertices are adjacent. So yeah, so it has a certain property here. P is the probability that two vertices are adjacent. Probably I can delete this condition because when I say that p is a probability, then it follows that it is strictly between, not strictly, but it's a number between 0 and 1 inclusive, right? So yeah, that's another example of a degree distribution. And as like the Poisson distribution, they are not usually found in applications. All right. But the more interesting type of degree distributions for us would be the power law distributions or exponential distributions. Power law distributions, or sorry, exponential distributions usually follow this form. Where's my counter? Okay, there you go. So here I'll start with exponential. So exponential, it's hard since I'm not drawing on the screen. I'm using a separate tablet. But anyway, for exponential distributions, here's the formula. It's P sub k is equal to a constant, a normalization constant C, a parameter in your problem, times e to the negative alpha, another parameter, times k. And yeah, the condition here is that that alpha is greater than 0 for exponentially distributed degrees. Okay. On the other hand, power law distributions, its formula would be P sub k equals C times k to the negative alpha. And here, usually in applications, alpha is a number between 2 and 3. Okay. Now, power law distributions are the ones that we often see in physical networks, like in network of airports or transport hubs. Cell metabolism also are modeled as as networks with power law distribution. For instance, E. coli metabolism of in the cell has alpha equals 2.2, and even some other synthetic networks, like if you will model the citations in journals like physics reviews, you will get a power law. You can fit a power law distribution with alpha equals 2.3. Okay, so that's why these are some instances, some networks wherein the degree distribution is very important, because in degree distributions we can deduce some properties of the graph by knowing what kind of distribution we have for their degrees. Now, some other examples here: collaborations in math papers, citation indices, even interaction between websites. So one website having a link to another can be modeled with a power law distribution. Internet traffic can also be modeled as a network with power law distribution. US power grids can also be modeled as a power law as a power law distribution, but I think this is more of a exponential distribution. You can fit an exponential distribution better for US power grids. And for protein interaction, I think it's also power law distribution. So here are just some examples of the things that we can do with the graphs, knowing the distribution of their degrees. Okay. So any questions about degree distributions? These are more probabilistic properties, and perhaps when we do random seeds or random or experiments with random components or with some essence of arbitrariness, we can use them, right? So we will be invoking these again. So it feels that I'm giving you a crash course in graph theory, and it's not just strictly graph theory, but I'm all over the place in graph theory. So it seems it's just a patch of different properties, but this will come into play whenever we look at algorithms, like in machine learning, in particular in classification and clustering algorithms. Okay. Now I'll do a quick leap to another particular topic in graph theory, which is a way of representing a graph. Because as far as this point, we're just using pictures to represent graphs, right? We all do the computations using pictures. But what if you want to store graphs in a computer, right? One way to do so is by constructing an adjacency matrix. The adjacency matrix simply keeps track of what are the edges or which vertices are connected via edges. So we'll just need to make a rectangular arrangement of numbers. Essentially, I will put a 1 on the entry in the matrix, right? Say in the ith row and the jth column, if there is an edge pointing from vertex j to vertex I. And I will put a 0 if that's not the case, right? So let's look at a particular illustration here. For instance, this is the adjacency matrix for the graph you see on the left. So this is the the blue numbers. Actually, this is the matrix for the adjacency matrix for this graph. So it's a 4x4. This is a 4x4 matrix. So it's a square matrix with n rows and n columns, because each of the rows and the columns will represent each of the vertices. That's why we can label them vertex A, B, C, and D. So the columns and the rows. Now, if you look at the graph, there is no vertex joining, or there is no edge joining vertex A to itself, right? So that's why here we get a 0, okay? But if you look at the vertex, at vertex B, so vertex B is over here, and there is an edge joining vertex A to vertex B. So that means the entry, or starting with column A and row B, will have entry 1, because there's an edge pointing from vertex A towards vertex B, right? Now, if you look at this entry, the entry on the second row, fourth column, this will tell us it's a 1. So this tells us that there is a vertex, there's an edge starting from vertex D pointing towards vertex B. So, and that vertex will be BD. Actually, when I'm talking about a simple graph, the ordering doesn't matter, right? But I want you to get used to the convention that the starting point for an edge is the column label. But again, that doesn't make sense for a simple graph, because there is no starting and ending starting point for an edge, because it's bidirectional. The consequence of the bidirectionality of the edges in a simple graph is that the adjacency matrix will be symmetric. So that means if you fold it along its diagonal, by the way, the diagonals are always zeros because we don't allow vertices to be connected to themselves, right? If you flip the matrix along the main diagonal, right, they will coincide, right? So I have a 1 here, so I'll have a 1 here. I have a 1 here, so I'll have a 1 here. I'll have a 1, 0 over here. If I flip that, I'll get a 0, 1 over there, and so on. So essentially, it's a symmetric matrix, okay? So the adjacency matrix of any simple graph is symmetric, okay? And then if you want to know what's the degree of a vertex I, you simply need to add up the row, or the row numbers, or the numbers in the corresponding row, or the numbers in the corresponding column, right? Remember, the degree of a vertex I is basically how many edges is connected, how many edges are connected to vertex I. And note that each number here, there's a 1 if there's an edge connected, or to vertex A, right? So from here, I can say that KA is basically 0, the sum of the column. It's 0, the sum of the column. Let me just clear here this one. Right. So to get KA, we simply need to add the column corresponding to A. So we have 0 plus 1 plus 1, so we get 3. Okay. The degree of B is 2, the degree of C is 1, the degree of D is equal to 2, right? And then from there, you can compute for the degree distribution, right? Because you can just take note and do the computations as what we did earlier, but without looking at the graph anymore, you look at the adjacency matrix. Now, a similar thing can be done to get the adjacency matrix of a digraph. But this time, we need to be very particular about where a certain edge starts and where it will end, okay? So for instance, in this digraph, we will have the following adjacency matrix. Now again, the diagonals are all zeros because we don't allow edges to connect on a vertex to itself. Now there is a 1 on row B and column A because there's an edge starting from A going to B. Starting from A going to B. There you go. That's the edge AB. So there's a 1 there. But look at this. There is a 0 on BA. Oh, sorry, on AB. Right? The flip side or the course the number where this guy will land if I will flip the matrix along the main diagonal. So here, this is BA, there's a 1, because there's an edge starting from A, ending in B. But the flip side is AB. It is 0 because I don't see any any edge starting from B and ending in A. And this clearly shows that the adjacency matrix of a digraph is not necessarily symmetric, right? Because having an edge from A to B doesn't guarantee the existence of an edge from B to A. Okay? Does that make sense? I hope it does. Let me know if you have some questions. Now, if I want to know KA incoming, how can I compute KA incoming or the incoming degree of vertex A by just looking at the adjacency matrix? Remember, the incoming degree is the number of edges going towards the vertex A. If I am only looking at the adjacency matrix, how do I find that? Or in general, how do I find the incoming degree of a vertex?
Yes, sir. You know,
Yeah, go ahead.
and according to the definition of the incoming degree, if we want to find for E, then we say it's 2 because we have from vertex T and vertex C going to E.
Good. So it's gonna be 2. How did you obtain the 2? Did you look at the picture or did you look at the
Yes,
adjacency matrix?
and both, and because if you look from, because we have A to C and D, and then we have okay, if you look, then if we want to see it incoming to A from the diagram, then we look, yes, then we look at the row from 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 D from D to A, you have 1. Then from
This
C
one.
from C to A, you have 1.
Okay, good. So yeah, that's a good way to compute the to find the incoming degree. But if I will just restrict myself to looking at the adjacency matrix, I can simply add the rows, the entries in the row corresponding to A. So essentially, I can do it this way. So the incoming degree will be the sum of all the entries within the row. So 1 plus 1, that's going to be 2, as your classmate computed earlier, the incoming degree is 2. And it makes sense, right? Because these numbers will be 0 if there's no edge going to A, right? And it will be 1 if there's an edge going to A. So if I add the numbers in the row, I will get the incoming degree for A, which is 2. Now, the incoming degree for B is equal to 1 because there's only one edge going to B, and that will start from A. And you can verify that by looking at the digraph or the pictorial representation of the digraph. So this is also 1, and then this is also 1, right? And similarly, the outgoing degree will be given by the column sums. So here will be my outgoing degrees. So 1 plus 1. So the outgoing degree of A is 2 because there are two edges that starts from A. Remember, the column label tells us where will an edge start, right? The outgoing degree of B is equal to 1. Outgoing degree of C is 1. Outgoing degree of D is equal to 1. So essentially, once you have stored your matrix, once you have stored your graph using an adjacency matrix, then you can do the computations. You can compute for the degree for the degrees, be it just the degree for simple graphs or the incoming and outgoing degrees for digraphs. And after that, you can also compute the degree distribution. So this is very handy whenever working with larger networks because you're looking at the diagram and counting edges, etc., will be very cumbersome whenever we have a very large network, right? Or a graph with a large order and large size. So basically, we can store those information inside an adjacency matrix and then write a simple code or a simple line in your code to compute the incoming degree, outgoing degree, or the total degree, or just the degree for simple graphs, and then we're set to go with the analysis. Okay? Right, so everything here are in the slide, so don't worry if you can't read my handwriting. They are still there. I just find it better if I do it real time. Okay. Okay. Right, maybe I can skip this one. Okay, sparse networks. Okay. Oh, basically, yeah, maybe this is important. Most real networks are sparse. When we say a sparse network, it means that the adjacency matrix has a lot of zeros. But what's the consequence of that? When the adjacency matrix contains a lot of zeros, that means the size of the matrix is small. There's just a small number of edges, meaning there is just a small number of connections between the vertices in our graph. So it's sparse because its adjacency matrix is sparse, meaning there are lots of zero entries in there. Now, the antonym of sparse networks are dense networks. Dense networks are networks with a very huge size. There are a lot of edges in these kinds of networks, right? So the maximum number, what do you think is the maximum number of edges in a graph? Clue, it will depend on the order of the graph. So what do you think is the maximum number of edges in a graph if it has n vertices? Can somebody give me a formula? The maximum number will be attained if a vertex is connected to all of the other vertices, right? And that's what we call in graph theory a complete graph. A complete graph where a vertex is adjacent or is connected by an edge to all other vertices in the graph. So anyone who remembers the formula to count?
Can we use combination?
Sorry, come again?
Can we use combination?
Yeah, you can use combination. It's what? What combination what?
Yes, that is if I want to try for so with n vertices we could we say 2 raised to the power n times 2 the combination of n taking 2 at a time equals to 2 raised to the power n times n minus 1 over 2.
Yeah. I think you're on the right track, or I just misunderstood, or you're trying to simplify it. But the simple answer is n taken 2, right? N combination 2. Because you'll just be taking how many pairs, how many possible pairings can I make between the graphs, right? So I have n vertices and I need to pair them up. And I will assign to each of the pairs an edge. So it is essentially n taken 2, right? Because I will decide how many edges should be there. And an edge should have a pair of vertices. Now, we use combinations because we don't care which comes first, right? I just need to draw all possible combinations of 2 vertices and draw an edge between them. Oh, thank you, Z. Z commented on the chat box and taken 2. Right? So yeah, it's a combination again because we don't care about the ordering, right? So is that good? Okay. So that means the size of a graph is directly related to its order, or I mean, it is a bound for the size depends on the order. It can go as low as 0 for an empty graph. We say an empty graph is a graph with no edges. And the maximum, the most dense of them all are complete graphs whose size is n taken 2. Okay, or n times n minus 1 all over 2. Right. But in practice, most networks are sparse, right? So, and that is a blessing for us because computing things involving a sparse matrix is much more efficiently carried out using computers than when you're doing with dense matrices. Okay. Now, maybe the last point I want to share with you today would be weighted graphs. So, how do we store weighted graphs? Well, how are weighted graphs different from the graphs that we have considered now? We have considered before. Weighted graphs assigns a weight to the edges, which could represent cost, could represent distance, right? So, for instance, if I'm gonna interpret the vertex starting from A and ending in B, it has a label 3. It has a weight 3. So that means there's a penalty of 3 units if I want to traverse this edge, if I want to go from A to B. So for instance, this could be a province A, this is province B. 3 could be the distance, 3 kilometers between them. Or that for instance, if you want to go through a network starting at computer A, ending in computer B, you will need to spend $3. So something like that. So there are several interpretations for weighted graphs. Now, adjacency matrices for weighted graphs can also be constructed, but at this time we will take into account what's the weight. So instead of just putting a 1 whenever there's an edge between vertex A and B, we will put 3 inside the matrix because the entry will be the weight. So we can keep track of the weights for the particular edge. Okay. And we'll still put a 0 whenever there is no edge between the two graphs. Okay. So in this example, we see that there is a 5 in column B, row B, because if you look at the edge starting from vertex B and ending in vertex B, that's this guy, you have 5 units as weight. Now we get the 6 here because the edge starting from vertex B, remember the column is always our starting point. We start at B, we end at D, so that is this edge, and it has a label 6. That's going to be the entry in my adjacency matrix. Okay. Okay, so the slide says rest for 10 minutes, but I'll give you a rest for how many days? For more than how many days? I don't want to count. So for some days, because I'll stop here, and next time we're looking at paths and distances, and we will perform one of the most famous algorithms in graph theory, the Dijkstra's algorithm, which will give us the optimal path from one vertex to another. Okay. But before I dismiss you, do you guys have any questions?
Sir, I have a question in the chat po.
Let me check that one out. Yeah. Do you need to modify some of the formulas? Yes, Z. For instance, say the formula for what formula? Oh, I think all the formulas that we have so far will all hold. Hopefully, I didn't forget any of the formulas that we considered, but everything that I'm thinking of right now doesn't need any adjustment. For instance, we said that the sum of the numbers in a row tells us the incoming degree of a vertex. Then that will still be true if we allow self loops, because you'll just put a non-zero number inside the diagonal of that matrix, and that should be fine. What are the other formulas that we considered? Well, degree distribution, the probability, that still holds. well, the size, the formula for the size of the matrix given the size of the graph based on its size and order will still hold, but we are really counting self loop. So yeah, I think there are some the formulas that we consider today still holds whenever we have self loops. So you can correct me if I'm wrong, but on top of my head, I don't think any formula needs adjusting. Stevens, you have a question?
Yes, sir.
Go ahead.
And when we when you were discussing the binomial distribution, you use n minus one
Uh-huh.
and Yuki.
Right.
Yeah. Why was the reason for the n minus one actually?
In that particular case, because yeah, maybe it's related to this question, because I'm not allowing a graph to have a self loop. That's why I need to subtract one from it. So because if you are on a vertex n, I am just if you have an order n and I'm looking at the probability I'm looking at the probability of the probability of a certain vertex to have degree k, because the maximum degree will be equal to n minus 1, because we don't allow self loops, right? So if you have, say, if you have 5 vertices, the maximum degree will just be equal to 4 if you are not allowing self loops. That's why you need to subtract 1. But thank you for pointing this out, because if you are allowing loops, then the binomial distribution for the degrees will have n taken k times p to the k times 1 minus p to the n minus k. Right. So thank you for pointing that out. That's
Okay, sir. But that means in the last problem that we had to do with weighted, because I think we took a distance on the same vectors. The last portion you discussed. Hello?
hello. Which one? The last?
Yes, the last one, the weighted.
The
When
weight.
you
Uh-huh.
Yes, yeah, you can see vertex B
Uh-huh.
checking from, so meaning that we are relying on loop, right?
Mm-hmm.
So in this case, then if we are using probability distribution, then it will be the normal, we say the normal binomial distribution. If in case,
Yeah, I think so.
okay,
Yeah, that's why it's very tricky when you have self loops. That's it's quite, I mean, it's quite what's the term? It's quite rare that we allow self loops, right? So because in physical networks, if you want to go from the same place to the same place, there should be no associated cost for that, right? So it's everything becomes tricky when we allow self loops. That's why we usually restrict ourselves to simple graphs and digraphs at the most, right? So, but this is just to complete the theory. Yeah. I'll double
thank
check.
you, sir.
Yeah, I'll double check the formulas for the distributions whenever there are self loops, because yeah, they might be very tricky. All right. Okay. Other questions? Everything's good. If that's the case, then I'll see you guys on when? I'll see you guys on Tuesday. I will be on. Oh, by the way, I don't know if I mentioned this already to you. Next week, I'll be on official travel. I'll be in the United Kingdom. I'm not sure with my schedule there yet. I will know it over the weekend. If I can meet you via Zoom, that will be great. But in the worst case that I won't be able to meet you because of time difference, then because I might have schedules in the morning there, if I can't meet you live, I'll give you a video recording, but I will be open for consultations for some time, right? I'll give you sometimes probably in Tuesday and Thursday, uh, when you can meet me. via Zoom if you have some questions about the video that I will ask you to watch, or the video that I will record. Or if I will record it while I'm in the UK, I can send you the invite to that. And if you're free, you can join, but you're not required to join. But I'll give you the recording. All right. I hope that's fine. And with that, I guess we can call it a day. Thank you guys for coming today. I know it's a bit of probably you probably experience information overload, but I hope that's fine. I'll give you a copy of the slides for you to review it on your free time or whenever you need it. But yeah, let's take a rest, and I'll hopefully see you next week. All right. Bye, guys.
Yeah. Bye. Thank you, sir.
All right. You're welcome.